screen here.
You should be able to allow to share screen. If not, I'll make you co-host if that's required.
Okay, are you seeing this?
Yep, loud and clear.
Okay. Okay, and then can you see my cursor? That's the other.
I can see your cursor too.
Okay, excellent. Yeah, so thank you, Marco. Thank you very much. What I'd like to talk about today is observations and modeling of global scale high latitude filament eruption. And so this is kind of a continuation on work that we've been doing for a while now. The standard model for CMEs is basically known as the CSHKP model, and depicted in this kind of cartoon here at the right. So basically what happens is you've got some energized flux that is either in the form of a flux rope or highly sheared fields or some combination. And that energy imbalance of all that concentrated magnetic free energy in the shear above the polarity inversion line, causes the magnetic fields want to expand. That's a pressure imbalance. And as this thing rises slowly, you form basically a vertical current sheet. And when reconnection kicks in at that current sheet, that allows the whole system to kind of rapidly reconfigure itself to get rid of that stress energy. I mean, the sun, for some reason, has figured out that the way to get rid of, all this kind of sheared, twisted field, it's energetically favorable to blow it out into the solar system, into the heliosphere. Here's an example of basically a two-ribbon flare. The red and blue contours are positive and negative magnetic polarities in and this is a kind of active region. And you see all these bright striations here are the post-eruption arcade. And so these are loops connecting the positive and negative polarities here. And this is underneath the erupting structure. And so these loops are bright because there's a bunch of energy released in the reconnection region, and energetic particles come down and hit the chromosphere, cause upwelling and thermalization. And so you can get temperatures of 10 million Kelvin in this process pretty easily. What this looks like dynamically is shown in this simulation that we did in 2016. So this is a kind of classic slow streamer blowout CME. You can see that we've stressed the field lines. These white field lines are kind of the filament channel. The yellow field lines were sort of the overlying helmet streamer closed flux that was kind of restraining all of this energetic field down here. And as that slowly opens up, it allows the expansion and then the formation of this current sheet. So the red field lines are basically the boundary of the helmet streamer. And so you get this kind of swelling of the helmet streamer, up to days in advance. And as the overlying field is sort of opened up into the solar wind, that allows the stress field to continue to rise. Then you get this current sheet. And once the reconnection kicks in at this current sheet, then all of a sudden you can eject all of that twisted field. So that's a very pretty field line movie. But the question is, does that look like what the sun actually does? And the answer is yeah, surprisingly. So in the upper right here, we've got a comparison of basically the the core one white light density structure. And if you squint, you can see kind of an X point here. That's what this blue arrow points to. And in fact, in the MHD model, and so this is synthetic white light made from the density cube. The MHD model, you've got a kind of X point here too. I mean, this is and it's about the same height in the simulation, the observations. Down here you've got basically the three-part structure. This is running difference a little bit further out. You can see the kind of the remnants of the inflated helmet streamer being blown out here. And you can see this cusp concave up region in the back, connecting to this current sheet. And that's a similar kind of structure that we get in the simulation. Now, what you can do with the simulation that you can't do with observations is take this exact viewpoint and look at the magnetic field. And so, sure enough, you can now associate, different parts of the ejecta magnetic structure with various features of the white light. And so you can see some, disconnected flux here under the reconnection thing. And, when you view down, from the top down, you can see the axis of the flux rope. And was kind of because this was a slow eruption, there was sort of this herniated thing that happened before. So this just kind of proves that the viewing geometry is it helps to untangle from the observations. These simulations can help to untangle and interpret what the observations are actually showing. So that was our simulation from a couple years ago. And what we're doing now is we're going to be modeling this event. And so this is kind of the next sort of version of that same simulation. So what I've got here is this event was July 9th and 10th, 2015. These are all SDO observations. So in the upper left is HMI, and you've got 3 different wavelengths of AIA. And in this event, the polarity inversion line of interest, which are these magenta contours, stretches all the way across the disk face. And so on this kind of global high latitude polarity inversion line, you've accumulated a whole bunch of that stressed magnetic field. You do have prominence material, which you can see down here in 304. There's this kind of faint cloud that's pretty big. It kind of fills the entire, 120 degrees of the 180 degree disk surface. And when we play this movie, you can see sort of a number of features happening in the different wavelengths. So there was the eruption. And if we go through kind of each of these things, you see the prominence material lifting off, and then you see it off limb and these kind of threads and filamentary materials twisting around each other. In 211, what happened? Let's try that again. In 211, you see a little bit of this material, but you'll see the dimmings. You'll see the dimmings happen, and then kind of refilling in of this brightness. And so, okay, this doesn't look like your standard flare, but we're going to show that with the MHD modeling, it does actually act like the magnetic fields act in the standard picture. So you've got these kind of 2 dimming channels, and then this slow filling in here. And you'll notice that this region of the disk in 211 corresponds exactly to this kind of bizarre stripe in 171. And so if you watch this stripe develop down here, you can kind of both see some off-limb stuff here, but then this thing goes from east to west, and it kind of acts like flare ribbons, in that it's a sort of narrow thing first, and then they spread kind of away from this polarity inversion line. And so this kind of dark, bright pattern here does correspond to kind of the boundaries of 211 filling up. So that's interesting. And we're gonna, because this is so large scale, we're gonna try to model it with our MHD simulation. So the features, and we've called these on-disk signatures ambiguous, because okay, in some ways they look exactly like eruptions, the kind of standard picture, but in other ways it's a little bit funny, and the whole event is super slow motion. So this eruption takes like a day um, to kind of go through. So here in 304, I've kind of highlighted the prominence material. You can see sort of this um, typical prominent shape kind of rising. And then here you've got, these barbs, or sorry, not barbs, but the filamentary threads sort of wrapping around each other. Also, there's some indication of the material draining um, down into this foot point during the eruption. Um, Here is that ribbon progressing across the surface, basically corresponding to the boundary of the post-eruption arcade. Um, Here in 211, you see the dimming. So both like the shape of the coronal hole here sort of changes. It increases, gets sort of more dark, and then kind of fills back in. And again, this dimming, uh, say, channel um, sort of propagates from east to west and fills back in again. So a quick note about chirality, because I know Olga's very interested in this. If you take a look at some of these filamentary materials, the strands basically rotating around each other, you can get a sense of what the chirality is, or what the sign of the helicity is, because of the crossing patterns. Um, and then the other clue here is that when you look at H alpha a couple days earlier, you've got a little bit of there's not a lot of prominence material visible here, but to the extent that you see some of it, you've got all these barbs, and they have a definite um, sense to them, right? So here in the movie, you can see crossing the filamentary threads crossing from the lower left to the upper right. That implies a right-handed chirality. And then if you stand on the positive polarity flux and look at the neutral line, the barbs are left-handed, left-leaning, which implies that the whole structure has a kind of right-handed chirality. And so because this is in the southern hemisphere, to get a right-handed chirality on such a large polarity inversion line makes sense. Okay, so here is that event in white light coronagraph data. And so what you'll see, this is C2 and C3, is the initial eruption here on the east limb. Then this kind of funny arcing stuff that sweeps from east to west. And then a secondary kind of eruption here on the west limb. And so this is, and you'll notice, okay, this is a slow eruption. This thing happens over the course of, a day. And in fact, because there's this kind of dichotomy in what appears to erupt first and then what appears to erupt second, the CDAW catalog, the LASCO catalog, actually has this thing listed as two separate CMEs. This first East Limb event, and then this kind of second West Limb event. And what we're going to show is that it's in fact all part of the same eruption, and this sweeping arc kind of right here is what connects it. And so in the low coronal signatures, all of that east to west propagation is mirrored, is also reflected in the east to west propagation in white light. And then here's just the snapshot frames of those same things. So you see this arc first, and then this kind of secondary eruption on the west limb. Okay, so enough of those observations. Now we're going to get to the good stuff. We run this 3D MHD simulation with ARMS, developed at NASA Goddard with Rick DeVore, Spiro Antiochos and company. We've got multi-level grid refinement. We choose to keep basically a static grid, but we can concentrate the grid points in the hemisphere kind of above the polarity inversion line of interest. Um, we initialize the simulation with, the synoptic map from Carrington rotation 2165. We happen to use Gong, but we could have used MDI or HMI or kind of anything. So this dashed line is kind of the day of the eruption, July 10th, and then this box is our kind of crude estimate of where the polarity inversion line is, stretching across the disk face. So you can see this is a huge source region. And when we look at the Gong potential field source surface extrapolation from this data, you can see that polarity inversion line lies right under the helmet streamer belt. And so this is, it's not a standard kind of dipole configuration, but it's very dipole-like in this region. And so this eruption is also similar to the example that we showed kind of right at the beginning. This eruption is also a streamer blowout CME. And so, okay, the first thing we've got to do once we've got that potential field source surface initial state is put a solar wind. So we do kind of the simplest thing you could think of, which is Parker's isothermal solution from 1958. And then we relax that for 100 hours in the simulation time. And that gives us the distribution of open and closed field. And it's not exactly the same distribution as the real sun, but it's not bad. So over here on the right, we've got synthetic white light in the sort of the steady state solar wind solution. On the left here is the, image processed coronal configuration. And you can see for the most part, we get a streamer here and then kind of this other sort of extended pseudo streamer type thing here. And so we're at least getting the overall magnetic configuration, somewhat similar to what the real sun's doing. And then if we zoom out a little bit, you can see this is the magnetic field configuration under our steady state solar wind condition. Zooming out even further, this kind of the C3 field of view. The green and red field lines are positive and negative polarity. And this yellow isosurface is the heliospheric current sheet. And so what you can see is just like in the PFSS version, once it's relaxed, you have this kind of big excursion here on the east limb. It's relatively flat kind of in front of you, but it is dipped below the equator, and then it comes up again on the west limb. And so, we've got, it's okay. I mean, we don't have the exact density distribution as the real sun, but we've got the magnetic fields doing the right kind of thing. So how do we make this filament channel erupt? In previous, in our previous simulations, we've just done, kind of the simplest thing you could think of, which is add ideal foot point motion and sort of introduce shear along the filament channel. We can't quite do that this time because our filament channel and the polarity inversion line here has got some real structure to it. There's these kind of bumps, wiggles, it kind of wraps around this sort of active region here. You've got multipolar configurations kind of right up against the, polarity inversion line that we're interested in. So we had to come up with some other way of basically introducing a large shear component along this neutral line. And so, Rick DeVore and Spiro Antiokos and company have developed this thing that they called Stitch, which is basically a statistical version of, Spiro's kind of funny helicity condensation model. And so what that means is we basically put in horizontal flux that follows the contours of BR. And so if you look down here at the bottom panel, you see this kind of circular intensity images, or the intensity pattern here are these circles. And if you could imagine sort of introducing a field line that follows this circle here and follows this circle here, they're going to reconnect and create a larger field line around both circles. I mean, this is exactly the helicity condensation picture, just on a very large scale. Um, and so what happens when we kind of add up all these spatial functions to like smooth, basically smoothly concentrate our boundary energy, kind of on this particular region, is you get so these are the time dependent field changes that are introduced as a source term in the induction equation. And so here's the dB theta dt component and dB phi dt component. And what you can see here is basically these circular patterns. So you've got this kind of clockwise or anti-clockwise rotation being added here, but all of these things add up so that you get a coherent introduction of basically, here's the phi component sort of all along the neutral line. And so we introduce this slowly, and the system evolves quasi-statically. And there's an effective foot point displacement speed associated with this, the electric fields that introduce this horizontal component. And that's on the order of 5-10 kilometers a second. I mean, so the sound speed down here is 150 kilometers a second. The Alfvén speed in the strong field regions is like, between 500 and 1,000 kilometers a second. So what we're doing in this with this, introducing this horizontal flux is, it's definitely still slow compared to this, the kind of characteristic speeds of the system. So what does this look like? Here is some field lines representing, basically from a couple different viewpoints, that filament channel after we've sheared, or done a fair amount of this horizontal flux injection. So you can see that we've got stretched field lines that basically follow the whole polarity inversion line all the way around. You've got some kind of overline field in yellow here that has less of a phi component. These field lines are color coded by basically the shear component, and you can see that the shear is concentrated more or less low down. There's unsheared field sort of above it, and so as this thing proceeds, you get exactly the same kind of picture we've seen before. You inflate the helmet streamer. The expansion has caused the formation of a current sheet kind of in and underneath the rising flux of the filament channel. And then once that reconnection kicks in, this whole thing erupts. And so the takeaway message here is, you'll see the eruption happens on the east limb first and then propagates all across the polarity inversion line. And so that's very promising in terms of the kind of overall global behavior seems to be what the observations show, that the eruption happened first on the east limb and then sort of progressed. And so okay, there's a couple other things to note here. The eruption does not open the flux all the way down to the polarity inversion line. So even though this has managed to get rid of a lot of this twisted field, there's still some residual, you'd say, non-potential component here, and that's in fact pretty common on the real sun as well. You can often see these filaments reforming after eruption relatively quickly, or you'll see like half the filament erupt and half of it just kind of stay in the corona. So if we look at the energy evolution of this simulation, so that movie was from 160 on, so that was the eruption. And what we had done before that was basically build the filament channel with this, sort of this energization, this horizontal flux introduction here. So this dashed line is the stitch profile magnitude. It's basically here just to kind of show when we've turned on this horizontal field injection, when we've ramped it down to 0, this builds up a whole bunch of free magnetic energy. Oh, the other thing that's worth noting is that this leaves the radial field exactly the same, so that kind of any accumulated magnetic energy represents free magnetic energy because the boundary condition on BR stays uniform. So you've got this increase of free magnetic energy. We let it relax, and so there's some reconfiguration of the field. There's some expansion. There's kind of some reconnection. But this thing settled down, and the energy, after a kind of slight drop, levels off. Now, so that gives us the stressed filament. Now, in order to erupt it, we've just kind of added a little bit more, energization. So our second phase is lower amplitude. It's a little bit shorter. We ramp it up, we ramp it back down. And sort of on the way down, we've the accumulated free magnetic energy has basically hit the threshold where it is now more favorable to erupt. And so that's what it does. So the reconnection kicks in. You've got this kind of rapid expansion. The reconnection accelerates all of that plasma out of the low corona. And what I've colored in yellow here is basically the time between the maximum free magnetic energy and the maximum, kind of global kinetic energy. And we've called this the impulsive phase of the flare, because you've got this rapid drop of, 3 times 10 to the 31 ergs, and then this kind of rapid increase in kinetic energy over the same time period. And then as the kinetic energy comes down, this is the erupted field kind of leaving the domain. Okay, so during the impulsive phase of the flare, one of the things that we're kind of most interested in is the reconnection and how the reconnection proceeds. And one of the reasons that we're interested in that is because it's one of these quantities that can be used to relate the eruptions seen at the sun to things you measure in situ in space. And so these ICMEs are measured in the heliosphere. They often have this flux rope type structure. That flux rope structure has a flux content, and then relating that flux content to what you observe during the reconnection phase of the eruption is kind of ongoing work. There's definitely a real connection there. Now, you can't measure the magnetic fields in the corona, but you can measure the evolution of the flare and the kind of progression of the post-eruption arcade. And you can calculate how much flux gets swept out by the ribbon motion in time. And so we've done that here. And you'll remember that the flare arcade didn't exactly look like a standard eruption, but we did have kind of indications that same process was happening at a much, you'd say, less energetic way. And so on the upper left here, what I'm going to show is, okay, this is BR from the simulation. On the upper right is synthetic EUV emission that we've used the same AIA color scale. And so you're going to see here, we're going to color the pixels of reconnected field. And so you'll see as this progresses, you get basically the flare reconnection and the flare ribbon motion all along the polarity inversion line. And it's colored in time. So when a pixel has reconnected, that means a field line has changed its length from that foot point by, I think, something like 3 solar radii or something. And you'll see this reconnection also propagates more or less from east to west. It's pretty fast in the simulation, but you do see that kind of zipper effect in the observations as well, where you have a rapid formation of the flare ribbons kind of along the polarity inversion line, and then a slower advancing of those ribbons sort of away perpendicular. And then if we look at, this is line of sight integrated density. If we look at this evolution, we see there's definitely some features of the observations being reflected here as well. So you'll remember these kind of two channels of dimming that form right at the eruption, and then a kind of slower filling in of the evacuated filament channel as it kind of returns back to the material during the flare, kind of gets reintroduced to these newly reconnected field lines. And this even more obviously than the reconnection pattern has this east to west propagation. It's really quite, anyway, if you're a simulation person, you look at this and you say, wow, that's reproduced the observations exactly. And so we can calculate what the reconnected flux is, given this pixel mask. And so that's what I've done here at the top. The black line is reconnected flux with time. And then the blue line here is basically the derivative. So it's the reconnection rate. And then the yellow bar is that same kind of impulsive phase of the flare. And then we've plotted the global kinetic energy to kind of put everything in context. And so you'll see what happens is the reconnection actually starts first and remains kind of slow, but you are sort of accumulating reconnected flux. When the reconnection rate jumps like pretty rapidly, you both increase the amount of reconnected flux kind of immediately, but you also start to see the eruption signatures in the kinetic energy. And so what you could say here is the very common phenomenon of sort of a slow rise phase and then a rapid acceleration phase is reproduced in our simulation. I mean, this is the field stretching out, and then the reconnection kicks in and transitions from sort of slow to fast, and that really just allows the whole rest of the eruption to proceed. And if you take a look at the observational version, okay, there's some difficulties here because all of the machinery for calculating reconnection flux from observations is based on this kind of bright ribbon emission. But if you've got this sort of faint, diffuse stuff happening in time, the best we could do with this particular event was basically outline the southern portion of the polarity inversion line, because there was all this kind of emission happening up here that sort of blocked the development or the kind of the ease of putting these contours. So up here is the sort of the overall pixel mask that develops in time, kind of along this channel, the southern hemisphere portion of this channel. And then here's the time evolution in the same sort of color scheme, where you see it, the very first parts of the reconnection happen close to the polarity inversion line, and then in time it fills in perpendicular. So here is the actual numbers. Once you take basically this area and you times it by this magnetic field, is you get a sort of a more gradual rise, and then eventually a kind of a little bit of a hump, and you get a value that's about 2.5 to 3 times lower than our simulation. And so you can see here we've got about 2 times 10 to the 21 Maxwells in that we've estimated from the observations, and then up here it's kind of more like 7 times 10 to the 21. Now, partly that's because we've calculated too much reconnection flux in the simulation. So you can see that up here you've got all this, these purple dots outline the open and closed field boundaries. And so you've got both kind of reconnection with this flux system up here. And then if you remember, this was where the coronal hole on the upper right-hand side, or the coronal hole extension, the low latitude extension of the coronal hole up here. And so we've got a bunch of interchange reconnection happening all over the place in the simulation. I mean, obviously that's happening on the real sun as well. but we're not capturing it with this estimate. And so just for fun, we said, okay, well, what if we just take a kind of this orange region over the main part of the polarity inversion line and look at the flux evolution here. And so that's the orange, ROI's region of interest here. And so you can say this is actually is sort of surprisingly good at reproducing, our observational estimate. I mean, so this region has 2 times 10 to the 21 Maxwell's worth of flux reconnected. And in fact, the transition in the simulation from kind of slow to fast happens about the same time as the peak, once you've lined it up, as the peak reconnection rate in the observations as well. So obviously there's a big difference between this purple curve and the blue curve. But the fact that they have a kind of peak increase at, sort of 17, 18 hours into the eruption, that was interesting. That wasn't expected. And it makes me think that whatever it is that we're doing is kind of like reality. So stepping back a little bit further, we've seen the synthetic white light imaging from the simulation. And so here is the eruption. And what you can see here is, again, we've got the same kind of large scale evolutionary pattern in the simulation reproduces basically the large scale evolutionary pattern that the observations did as well. So you've got the eruption happens first on the east limb. You get this kind of arcing thing, and then you get what looks like a secondary eruption on the west limb. And that's interesting because if you remember the Filament Channel movie, there wasn't 2 separate eruptions. It was just a continuation of the eruption starting to the east and progressing to the west. And so we've actually got, kind of features of both of those things here. And so this is the snapshot version. And one of the things that you can do with these simulations is you can take an image like this, which looks like observations, and then you can look at the magnetic field, which you certainly cannot do with observations. But if we want to figure out where those white light features come from, it's definitely helpful to look at the evolution of the magnetic field. So this is the exact same viewpoint as the synthetic white light images from earlier. And so you can see the eruption starting here is kind of this herniated, complicated mess. But as it progresses, the rest of the filament channel opens. And you can in fact see it opening in time with this sort of sweeping motion. And what you can say is the right hand, or, the west limb side, well, that kind of bubble structure you saw on the west limb in the observations and in the white light part of the simulation, in fact, is this flux rope opening up. So you see the eruptions kind of come at you first from the east limb, and then as it passes, kind of out of the scattering region, you've got this sort of leg of the prominence eruption happening here, and that creates the secondary, kind of eruption looking like thing. And you can compare the dynamics. So here's the kind of standard height time evolution. In the top row is the simulation. So we've taken basically 2 cuts, sort of one on the east limb here and one on the west limb here. And we're going to compare that to the evolution from the observations on the east limb and on the west limb. And what you can see, and this is velocity versus distance, is our simulation is a bit faster, which makes sense. We had a higher acceleration phase. But the overall character is the same, and the fact that the east limb goes first and is a little bit faster than the west limb in both the simulation and the observations is reassuring. And then if you want to say, what does the structure look like at 1AU? Well, one of the reasons that we were interested in this particular event is we did in fact have a corresponding ICME measured by ACE and wind at 1AU, basically 3 or 4 days later. So here we've got the data The top is magnetic field magnitude. Then you've got each components and their rotation in GSE coordinates, the angular, the magnetic field angular evolution. Here's velocity and here's density. And you can see at 1 AU, it's not a fast eruption. It's about 450 kilometers a second, kind of in the main flux rope region. It does drive kind of a weak shock here, and you get the rotation sort of in the central region, and there looks to be some real kind of sheath fluctuations here and some density pileup. So you can fit a kind of simple flux rope model to this rotation. You get these particular parameters. But what I wanted to point out is, basically as time, progresses on, the flux rope orientation is such that it's basically, you get the southward field first, and that rotates smoothly into a northward field at the end of the rope. And then you've got a kind of singular sign of the central region pointing west here. And so if you look at this cartoon down at the bottom, we basically get, I've tried to illustrate this rotation here. So you've got southward field at the beginning, kind of westward field is the axial component, and then you get the northward field of the twist kind of at the end. We get a fairly large impact parameter during this fit. We get right-handed helicity, that's the southwest-north type. But the fairly large impact parameter means you're far from the flux rope axis. And so that's what's represented here in this cartoon. And so if you said, okay, how well does our simulation reproduce that particular field rotation? Okay, well, we don't run it out to 1 AU, but we can look at what the structure is at, kind of 30 solar radii, 20 solar radii. And this will be useful for, looking at the Parker Solar Probe data. So here I've taken a number of cuts through our structure at, our erupting CME at a single snapshot here. On the left is the meridional plane, and on the right is basically the ecliptic plane, and so that's kind of semi-translucent, so that you can see all the field line structures here. And so here we've got basically 5 radial cuts in the ecliptic plane through various parts of this erupting structure, and that's what we've plotted here as a kind of time series. And so here, because this is actually a snapshot in space, time would be from right to left. But you can see that we've got a classic bipolar signature in the BZ component. So it's first south and then north, and then a kind of single polarity increase corresponding to the axial field component here in BY. And so when you look at the angles, you have a very similar kind of evolution. And so comparing that structure to the observed ICME at 1 AU, here's south, here's west, here's north, here's south, here's west, here's north. So, okay, skipping the entire heliospheric evolution, our simulation does in fact give you the same kind of rotation that we see at 1 AU. And so overall, I think that's pretty good. So to finish up, I mean, the magnetic field structure and the orientation of the CME is kind of the mission critical link between what you observe in situ at 1 AU or at Parker Solar Probe or kind of any given spacecraft, and what you observe remotely on the sun. We've called this event quasi-stealthy, in that it's not exactly a stealth CME because you have a whole bunch of low coronal signatures, but it's not exactly a standard active region CME either. And so the ribbon stuff is a bit weird. The post-eruption arcade is a bit diffuse. The white light structure is ambiguous in that, you could mistake what was going on. But doing these kind of numerical simulations is really useful for both, kind of the physical interpretation of the eruption as it's happening and sort of disentangling the kind of line of sight effects in the coronagraph data. And then, the real ICME observation shows a flux rib structure with a relatively high impact parameter. And our model seems to get the rotation, more or less right. So that's kind of the end of the presentation, and I'll be happy to take questions.
Thanks, Ben. A virtual applause. And we're ready to take questions.
I have a question. This is Paulette.
Go ahead.
Yeah, I have all that.
Okay. Very, very nice, Ben. Thank you. I was looking at the timing of your transition from the slow to the fast rise phase.
Mhm.
And it looks like that's determined or happens about when you add that second burst of input.
Yeah, it's a little bit later, but yes.
If you varied that, have you done anything about seeing if you had put that in, 20 hours later or something? Would that delay the transition? Is that what causes the transition, that extra burst of?
Yeah, to the extent that if we continued to do nothing from 160 on, this would just stay there. This structure would be stable. It would sit here like this forever. And so we had to kind of kick it a little bit. And so with just a little bit more of this quasi-static slow evolution, you've now passed the threshold of, this highly energized structure is more or less stable to this highly energized structure now wants to expand into the solar wind. So yes, if we, I mean, I haven't taken this exact simulation and kind of moved this stuff around yet, but we could. But from earlier modeling work by like, Judy Carpin and stuff, if you turn off the shearing kind of before you've reached this threshold, things do tend to die down. And so, we wanted to make sure that we weren't, say directly driving the eruption with the boundary conditions, and we're pretty convinced that that's true.
Okay, thank you.
Yep.
But what did you mean by threshold?
Well, it's whatever this is on this graph.
Okay.
So
All right.
so here it's not erupting, and here it is erupting. So the threshold is somewhere between
Okay. All
9
right.
and 10 times 10 to the 31 ergs.
Okay, thank you.
Yep.
So there's a question from Brian Welsh here. Are you aware of any structural factors that cause the east to west progression of eruption, assuming 3D is unlikely to occur simultaneously along the entire sheared arcade? It's going to zip one way or the other. Could it have zipped the wrong way just as easily?
Okay, that's a good question. Yes, I think it could have zipped the wrong way just as easily, except that if you look at basically the structure of the magnetic field along this polarity inversion line, you do actually, like, you can see this strong field region here on the east limb. Because our energization is proportional to BR, what we've done sort of by accident is stress the east limb more relative to, say, this part of the polarity inversion line over here. And so we do inflate the east limb more than we, say, inflate the kind of central or west limb portions, which is why the eruption kind of starts on the west limb, or starts on the east limb, and then the zipping happens this direction. Had the energization been a little bit different, yeah, I think we could have, perhaps erupted it from the west and had the eruption progress to the east if we had have dumped a bunch of energy on this side. So yes, in some sense, it's kind of completely determined by the energy input pattern. On the other hand, the energy input pattern is observed, is determined by the observation, the observed BR configuration. So it's the sun did it one way, and I think we've more or less done it the same way the sun did it.
Okay, so we had Bimsen, I think, before, then we have Angelos Sudong, and we have also a question from Janet. Bimsen?
Thank you, Marco. I was wondering if this build up from the slow phase to the fast phase, it kind of reminds me like a sand pile avalanche analogy.
Mm-hmm.
You have any comments on that?
Yeah. I mean, I think that's right. I mean, the transition from kind of slow to fast reconnection is an open question. I mean, it's something that people are working on, both in simulations of all different kinds. I mean, mine's a fluids code, but people have looked at this kind of transition with, particle codes and kind of hybrid codes. People run these laboratory experiments to try to, look at sort of interacting flux tubes and kind of reconnection. So it's really what is a common occurrence in some of these reconnection simulations is that as you build up stress kind of along the current sheet where the reconnection happens eventually, you elongate it, and then everyone knows that like the Sweet-Parker solution for reconnection is kind of too slow to explain the observations, and so you do get one of the ways that the system kind of gets around that is by breaking up the current sheet into kind of many X and O points, kind of having this sort of plasmoid instability. And so that transition from kind of a slow linear phase to then this kind of highly dynamic nonlinear phase, we don't resolve most of those details in this particular simulation, but because the simulation is driven by the evolution of the external field, it's smart enough to kind of compensate and reproduce aspects of that actual, fractal reconnection scenario. I mean, it's at the end, all of that breakup happens because you're trying to transfer flux and mass through the current sheet in order to preserve the conservation equations. And so even if you've sort of don't have all the detailed microphysics of reconnection, your simulation is trying to do that. And so we get a kind of, we have seen plasmoid generation in, to the extent that we resolve it. And so I think that that's kind of related to this transition. I mean, it's really the reconnection is slow and then the reconnection is fast. And that's the, like you say, the kind of the avalanche is this transition, which is like thunk. So I do think that there are, analogs and kind of other physical systems that are similar to this.
So we are sure that this is
and we have a lot of other questions.
please.
So let's go with someone else. Just a comment. I think that, we've demonstrated that there's a degree of universality that kind of doesn't want, as long as the Lundquist number is big enough, you'll have that transition happening quite independently of what the detail is. And that kind of strengthens in some sense, the realism of your simulations. So let's go with Angelos, then Shudong, then we have Janet and Karen.
Yes, Ben, this is great. Looks a lot like what we expect, of course, and what we said in the papers in the past.
Yeah.
My question it has to do with the energetics that your CME is quite a lot faster than the typical streamer blowout. So what would it take to actually match that the actual observations? Because it's challenging to get something erupting for, as I showed, for 2 days.
Yeah, that's true. And in fact, this problem is the opposite of what most people have and what we've had in numerical simulations for a long time. Is usually you get these slow eruptions and you're like, dang, I wish I could get this 2,000 kilometer a second CME.
Exactly.
Okay, so that is an interesting question. I mean, I'm not exactly sure how we would slow it down, except that you could maybe try to, drive it a hell of a lot slower. And I think that there's probably some element of the background atmosphere that we don't have
Oh,
exactly right. So our density contrast between the closed
mhm,
field and the open field is, not realistic.
mhm,
It's there, but it's not, it's probably not what the real streamers look like in
mhm.
terms of, um, material sort of sitting above there.
Yes.
And also we have kind of under resolved the field structure too. So probably the overlying field is actually quite a bit stronger
Mhm.
than we've got in this particular simulation. I mean, our maximum field strengths up here are like, 20, 30 Gauss, and then, obviously on the sun it's kind of more like 300.
Mhm. Okay, makes sense. Thank you.
Okay, Shudong, and then I'll get to Janet's question and then Karen.
Hey, Ben, great talk.
Yeah, thanks.
So you mentioned that the filament appeared to be only partially erupted or reformed afterwards. So that kind of remind me of the work did by Sarah Gibson and Yuhong Fan, where you have a vertical splitting of the flex rope, which was tethered at the ball patch. Is this what's happening here?
Okay, yeah. So that's a good question. I mean, okay. I'm not sure that that's exactly what's happening here, but it's similar in that, the formation of. Okay, let me see if I can stop this here. So the current sheet doesn't open all the way down to the polarity inversion line. And so that's actually something that kind of we've always seen in every simulation. It would be pretty difficult to sort of open kind of the whole channel. If you did, yes, all of this other stuff would erupt too, but it's small. I mean, it's that the reconnection kicks in at some height above whatever this leftover field is, and so if you were to have a scenario where that height was like higher up, you'd have more of the sheared field just hanging around, or if it was lower down, you'd have kind of less. But I don't think that this process is, I would say kind of independent of the particular configuration. And so I could certainly believe that in, some of the flux rope models, yeah, you could get this sort of splitting of the flux rope. Here we have weak twist. I mean, it's some people would call this a pre-eruption flux rope, but it's unclear to me that there's really that much of a distinction if you have a kind of very weakly twisted structure. So I'm not surprised that they've seen that.
Karen Mugla.
I thought Janet was before me.
Okay, you noticed the correlation. Okay, so I read, Janet, do you want to say ask your question, or should I read it?
Sure, you can read it.
Can you imagine automating a global version of the simulation?
Well, I can imagine it. I'm not about to do it, but I can definitely imagine it. Okay, so the automated version of this, okay, there's you would say our particular form of energization actually comes out of work that Spiro and Rick did with Duncan McKay and his group in the UK. And so it was designed to kind of power global magnetofrictional modeling, and they needed to come up with this particular, say, statistical version of the helicity condensation for the magnetofrictional modeling in order to get the chirality of all those high latitude filaments correct. Because if you just do the standard differential rotation, meridional flow, and surface diffusion terms in the flux transport scenario, you tend to get like you get some of the filament handedness stuff correct, but you don't get all of it correct, or you kind of miss on the high latitude things in a way that you don't miss if you've got this sort of statistical energization pattern. And so in some sense, the automated version would be you take his global magnetofrictional stuff and you run that forever. And then you've built up basically these sheared field structures with the right-handedness kind of all over the sun. And I think they've done that. The problem is you don't get the eruption part of that. And so you can get these kind of slow magnetofrictional evolution scenarios where you're like, okay, that there should be an eruption here because you've got all this stress field and my magnetofrictional simulation is kind of ejecting it out of the top of the box. But it's too, it doesn't capture the dynamics. It's not going to capture the kind of the energy transfer correctly. So we're not there yet, but I could see us getting there. If you had some sort of like continuously updated global magnetofrictional code that was kind of running at CCMC, it's certainly, plausible.
Thanks, Ben.
Yep.
Okay. This is next. I'm confused. So
Karen?
Karen didn't.
Yeah.
Yeah. Sorry, I was way expecting you, but your silence kind of threw me off.
So you can hear me? Okay.
Yeah.
One of the things I wanted definitely to say, so I would definitely not consider this as stealthy in any way.
Right.
Because any kind of experienced observer will immediately see that, and you see, actually, in my opinion, if I look at the basic, from the observational point of view, all the basic signatures of a CME, I see almost all of them except for the X-ray peak.
Right.
So the big GOES peak. But that's typical for these large-scale quiescent filament eruptions. You find them many times that you don't get these peak in X-rays, but you still see the thing lifting off. You see the dimming, you see the post-eruptive loops, and you see the foot points brightening. And it's actually a very nice event, so a very, very large-scale big event. The other thing I was wondering is, so you said you had, maybe I missed that, the magnetograms that you are using. So you said that you have the magnetic field in the, so these were synoptic maps.
Yeah.
Okay, I see. Because I was worried your east limb active region is very far to the east.
Yeah.
And at that stage, I would not trust my magnetogram to show the right magnetic field because, okay.
Yep.
So because you said you're driving it with the magnetic field that you measure, but the east limb magnetic field measurement would not be good.
Sure. Yeah.
So you
that's
have
a fair point. Yeah.
Okay, so you have a synoptic map, which also means now the magnetic field in this synoptic map was measured a few days afterwards.
Yeah.
You're aware of that.
Yeah.
Yeah. Okay, so we actually do not really know what the east limb field really is at that time.
That's true. And I think it's okay in this particular scenario because we're kind of in the quiet sun region. Okay, that's most of the filament channel, but you're right, the kind of the eruption on the east limb is a little bit under-resolved observationally, and we may be missing kind of a fair amount of what's actually going on that side. But sort of in spite of that, I think we're doing okay overall.
Yeah. Considering how ill observed the limb is.
Right.
Yes.
Yeah, of course.
Of course. Okay, thanks.
Yep.
Okay, one final question, Milo. Can you unmute? Okay.
Yes, thanks, Marco. So very good, Ben. The question is, you showed all these simulations and how the energy got ejected and how they went into the CME. And if you go to, for example, slide 20, yes, what would you expect to be the consequences of that reconnection process for lower layers in the solar atmosphere, like, for example, photosphere or any subphotosphere layer, that in terms of the energy? Right.
So one of the things we said in the 2016 paper, which was an attempt to like simulate an actual stealth CME with virtually no low coronal signatures whatsoever, was that the current sheet was so large, and the kind of the portion of the helmet streamer you were blowing out was so large that the magnetic energy released during that portion of the reconnection phase, basically the eruption, you could calculate it as like pointing flux into the current sheet, and then that's got to go two places, down into the post-eruption arcade, and then into the eruption. And if you even said all of that energy goes into the post-eruption arcade, how much energy is that? Do you expect to see brightening? Do you expect to see plasma heating? You work it out, and it's just not enough. I mean, the field strengths are too low, and you get a number that's kind of equivalent to basically the amount of energy to heat the corona kind of anyway, so it's sort of like the 10 to the 5 or 10 to the 6, ergs per centimeter squared per second or something. I mean, it's kind of just enough energy to kind of make a 1,000,000-degree corona, and not really enough energy to heat anything up more than that. So this case is a little bit different than the 2016 case, but I think in general, the same sort of arguments hold. I mean, it's, okay, it's a few times 10 to the 31, which is kind of more energy than we had in the 2016 case, but also the current sheet is large because the whole thing that's erupting is the size of the sun. So you've kind of spread that energy density over, a good portion of the disk. And so it's not surprising to me that there isn't, like Karen was saying, like X-ray signatures or anything like that. There's probably some amount of particle precipitation, and there was definitely some heating in that. We did see the dimmings filling in, and that's probably sort of, in our model, it's just material coming in from the reconnection region into the newly formed post-eruption arcades. Probably on the real sun, it's some part that and some part stuff coming up, from the photosphere, from the chromosphere. So I don't have a sort of more detailed answer than that, but I think probably the real sun is doing a little bit of both.
Thank you, Ben.
Well, thank you, Ben, again. We've been, over a quarter of an hour beyond the hour, so it's been a really exciting talk, and thanks everyone for participating. Our next seminar will be in a month's time. We don't have a speaker identified yet, but it'll be the third Wednesday of April. So thanks again, Ben. Thanks everyone for participating, and have a great evening, day, afternoon, depending on where you are.
Great. Thanks very much.
Good afternoon. Bye.
Bye.